Welcome back to the Deep Dive. Today, our mission is, well, it's arguably the ultimate intellectual quest out there. The search for a unified theory of everything.
It really is. And we're not just sticking to physics here.
No, we're jumping into sources that connect ancient philosophy, modern science, and really the very limits of how we can even know what reality is.
It's a massive synthesis project. And for you, the listener, we're trying to trace this core idea of unity. What's the one irreducible thing that everything is made of?
So we'll be moving from, say, Democritus,
all the way through Descartes and Spinoza, right up to the physicists today who are trying to combine all the fundamental forces and, maybe more frighteningly, explain the 96% of the universe we literally can't see.
It's metaphysics and mechanics, all in one journey. Okay, so let's unpack this. Before we had tools like the Large Hadron Collider, the first search for the simplest components of existence, it just started with thought.
Pure deduction. And that takes us all the way back to ancient atomism. We sometimes forget just how huge this conceptual leap was.
It's about 2,500 years ago, right?
Yeah, 5th century BC. The Greeks, specifically Leucippus and his student Democritus, they proposed that all matter was made of these tiny, physically indivisible particles. The atoms. And their logic was, it was surprisingly simple.
It was that if you can divide matter infinitely, you never actually arrive at a fundamental building block, so the division has to stop somewhere.
Exactly. It had to stop. That final unbreakable piece is the atom. It's a pure argument against the absurdity of infinite regress.
And what's wild is how quickly they applied this physical idea to ethics.
Oh, immediately. Epicurus didn't use atomism to build machines. He used it to build a philosophy of happiness. He argued that since atoms governed everything, no gods were intervening in your life.
Which means you, and you alone, were responsible for your choices, your own happiness.
Yes, it was a way to make materialism morally actionable, which is just a fascinating application.
It really is. But this materialist quest for the atom pretty quickly ran headlong into spiritual and theological systems.
Right, and that's where we get the great metaphysical divide of substance theory.
So later Islamic scholarship, for instance, they adapted the idea of the atom.
They did, but they completely stripped it of its self-governing power. You see this in Asharite atomism, which was championed by the theologian Al-Ghazali in the 11th century.
And how? How radical of a change was that? Because the Greek atom was supposed to be the master of its own world.
It was a total reversal. For Al-Ghazali, atoms were perpetual. Okay, but everything else, all qualities, events, change, was temporary, it was accidental, lasting just an instant.
So nothing had its own causal power. Fire doesn't cause heat.
No. God creates the heat at the very instant the fire appears. This doctrine is called occasionalism.
So if I drop a ball, it's not gravity making it fall. It's God is constantly recreating the ball in a lower position, instant by instant.
Precisely. It makes nature completely dependent on God's constant intervention for every single event. It's a total unification of reality, but under divine will.
Which is the absolute opposite of the autonomous natural world the Greeks were thinking of.
Completely. Yeah. Now, let's fast forward about 6 centuries to Spinoza, who sought a different kind of absolute unity.
Monism, by basically equating God with nature.
Right. His vision, summed up in that famous phrase, Deus Mandora.
God or nature.
God or nature. It was truly radical. He said there's only one substance, God, and everything else is just a mode of that single substance. Mind and body, he said, are one and the same thing.
The ultimate philosophical fusion. How did his contemporaries react to that? Especially with the scientific revolution kicking off.
There was massive fallout. Spinoza was persecuted, his work was banned. This idea was seen as profoundly dangerous because it totally challenged the dualistic view.
The separation of the spiritual from the material.
Exactly, and that very dualism was what René Descartes, his contemporary, really cemented into Western thought.
Cartesian dualism. Mind and body are two distinct substances, even if they're closely joined.
But Descartes' real legacy for science wasn't just the mind-body split. It was his epistemological demand. Discard your unreliable senses.
In favor of mathematical deduction.
Yes, but, and this is so important, he also insisted that deduction wasn't enough on its own.
Right. He knew you needed experimentation to actually verify your theories.
Absolutely. And that recognition is what really pushes this whole philosophical search for truth squarely into the world of mechanics and physics.
Which is a perfect transition, because that philosophical search for the one thing, it evolves directly into the scientific quest to combine the fundamental forces of the universe.
And that search, well, it gets its first monumental win with Isaac Newton.
the Principia in 1687, it didn't just explain how planets move. It proved Kepler's elliptical orbits were a direct result of the inverse square law of gravity.
It tied the heavens and the earth together. One seamless mathematical law. The ultimate conceptual coherence for its time.
And we sometimes forget his foresight in other areas, in his book Optics.
Oh, it's incredible. He's already talking about how light seems to have both wave-like and particle-like properties, basically anticipating wave-particle duality centuries before quantum mechanics.
He was already thinking in these deep, unifying ways. But his theory of gravity, brilliant as it was, it relied on action at a distance.
Right, the idea that the sun can just, instantaneously affect Earth's orbit across empty space.
And that was a sticking point that eventually proved incompatible with special relativity.
It was, which is why Einstein's general relativity, or GR, was such a seismic shift. He gave us that key insight. Space-time tells matter how to move, matter tells space-time how to curve.
So gravity isn't a force acting across space, it is the geometry of space.
It's geometry. Total change from a mechanical universe to a geometric one.
And what's so compelling to me is how long it took to confirm it all. He predicted gravitational waves, but direct observation by LIGO, that wasn't until 2016.
Almost 100 years later. A theory so elegant its consequences span a century. Just incredible.
So GR unified mass, energy, and the fabric of the cosmos. But the quest didn't stop, it moved to the atomic realm.
And that's where physicists scored another huge victory, connecting two of the forces that govern particles.
The electroweak unification. So that brought together the electromagnetic force,
which governs light and chemistry,
and the weak nuclear force, which governs radioactivity.
And this was the major achievement of Salam, who shared the 1979 Nobel Prize. He showed that at very high energies, these two forces were actually just different aspects of a single electroweak force.
And he didn't stop there, did he? He kept trying to push it further.
He did. He spent years trying to include the strong nuclear force in what's known as a grand unifying theory, that drive for synthesis.
And there's that wonderful human detail about it.
Oh, it's a great story. He didn't just accept the medal. He took it to his former professor, placed it around his neck, and said it was the result of his teacher's love of mathematics.
It's a great reminder that even these grand, abstract theories are built on human connection. Okay, this is where it gets really interesting for me. Because even with these historic victories gravity, electroweak physicists are now staring at this just massive, overwhelming mystery about what the universe is actually made of.
We're talking about the 4% rule. It's a stark, almost unbelievable fact. When you catalog all the mass energy in the universe, only 4% is ordinary matter.
The quarks and leptons that make up, and everything we can see or touch.
Everything. A staggering 70% is dark energy and 26% is dark matter.
So let me get this straight. All our successful unifying theories, Newton, Einstein, the whole Standard Model, they only describe 4% of reality.
That is precisely the challenge. We've described the 4% beautifully, but the other 96% remains completely elusive.
It's like we've only written a local ordinance, not a universal law.
Exactly. And even inside that tiny 4%, there's another profound puzzle.
The baryon asymmetry, why matter even exists at all.
Right. In the Big Bang, photons should have created equal amounts of matter and antimatter-like electron-positron pairs. They should have all annihilated each other.
And turned back into pure energy. The end.
But they didn't. For reasons we still don't understand, there was a tiny, tiny imbalance. About one extra electron for every billion pairs survived.
And that 1 in a billion left over. That's everything. Every star, every galaxy, us.
The entire material universe is a cosmic rounding error, and we have yet to unify that concept with our models.
Which is why scientists are looking for these radical new ideas, trying to find synergy across different scales.
It leads to concepts like Lauren Nautel's work on scale relativity.
Which is the idea that scale itself is relative, right? Just like velocity is in traditional relativity.
Exactly. It's an attempt to find patterns that hold true whether you're looking at a nucleus or a galaxy cluster. And sometimes this involves, some surprising analogies.
Like the strong gravitational constant.
Yes, in some speculative models, they explore the idea that the strong nuclear force is actually a kind of strong gravity that only works on a tiny scale. It's a conceptual leap.
It's an attempt to link the very large with the very small, using analogy.
You see the same thing in models that compare cosmological systems to atoms. The hydrogen system analogy, for example, tries to relate the orbits of planets to the orbits of electrons. They're They're asking, are we just seeing the same pattern repeated at different sizes?
And the ultimate mathematical tool for seeing patterns repeat across scales has to be fractals.
For Mandelbrot's work, absolutely. He gave us a geometry of infinite self-similarity. A coastline, a cloud, you zoom in, and the details look just like the large-scale shape.
Fractals are key to chaos theory, showing how incredible complexity can arise from repeating very simple rules.
Powerful mathematical language for describing the unity of complexity, no matter the scale.
Okay, but this raises a really important question. As we find these huge multi-scale laws, how do we know any of it is unified? We have to look at our own tools, our epistemology.
That's a crucial turn. Let's look at the cornerstone of science, inductive reasoning.
Inferring a conclusion about a whole population from just a sample. The sun has risen every day so far, so we induce that it will rise tomorrow.
And David Hume raised the greatest challenge to this. He argued that the principle of induction itself, the assumption that the future will be like the past, can't be logically proven from observation.
Is that what he's circular reasoning?
Exactly. You're using past observations to justify your faith in past observations. So pure empiricism isn't enough for science.
You have to take a kind of logical leap of faith before you can even start.
Precisely. Hume showed that induction has to be accepted as an independent logical principle. It's a fundamental tool in our kit, but we can't prove it empirically.
So if scientific unity needs a non-empirical starting point,
Right.
what about moral and aesthetic unity? That brings us to Kant.
Yes, Immanuel Kant sought unity in those realms, completely separate from atoms and forces. He sought moral unity through the categorical imperative.
The idea that a moral law has to be a universal principle of reason itself. Act in a way that you could will your action to become a universal law.
And it has to be grounded in the goodwill, not in just trying to be happy. It's a search for universal ethical consistency.
And he applied a similar kind of thinking to art and beauty. For Kant, beauty isn't something in the artwork.
No, it's subjective.
Yeah.
It's in us. He defined beauty as the pleasure that comes from the free play of our imagination and our understanding. It's a non-cognitive aesthetic judgment.
So he unified these realms by grounding them inside human reason itself.
Yes, allowing us to find coherence in our moral and aesthetic lives while physics continues its own search for the theory of everything.
What a sweep.
Yeah.
From Democritus's indivisible atom all the way to Kant's indivisible moral reason. Before we wrap, I want to highlight a couple of just amazing historical details.
Let's do it.
Okay, the speed of light. In 1676, Ola Römer gets the first real estimate. And he does it not with lasers, but by watching Jupiter's moon Io.
Just by timing its eclipses.
By noticing that the timing changed depending on where Earth was in its orbit, he calculated that light took about 22 minutes to cross the diameter of Earth's orbit. That's cosmic insight on a shoestring budget.
It's staggering. And just as staggering was Arthur Eddington's foresight around 1920. The source of stellar energy was a total mystery.
And Eddington was the first to correctly guess the mechanism.
Nuclear fusion. The conversion of hydrogen into helium, deep inside the stars. Stunning foresight, long before there was hard data.
But sometimes, even a theory that's totally wrong can have a little piece of the truth in it.
And that takes us back to Lesage's mechanical gravity theory. It proposed gravity was caused by tiny, unseen particles pushing things together.
It was proven to be fatally flawed, right? It predicted that the heat from all those collisions would just vaporize everything.
It failed the heat test completely. And yet,
One variation of that failed theory suggested the absorbed energy could be what powers the stars.
exactly, it offered a possible mechanism for stellar energy long before Eddington correctly identified fusion. It's a powerful lesson. Even a failed framework can sometimes foreshadow the right answer.
Which leaves us with a final thought for you to consider. The search for the ultimate theory of everything is a search for total unity. But we know our most successful unifications only describe 4% of the universe.
So does the universe's overwhelming composition of dark energy and dark matter suggests that we have to fundamentally abandon our tools. The very framework we inherited from Descartes and Newton.
To grasp the other 96%, the deepest dive into reality might require us to rebuild our definition of knowledge itself.
Indeed. We'll be waiting to unpack that next chapter when it finally arrives.
Until next time, keep digging and keep learning.